Well, hello there everyone. This is KP the Math G, as you can see right here. It's been a couple of days since I've done a video, but I want to do one today. I am not sporting a cap for the first time in a while. So anyway, well, it's Sunday, so I'm not wearing caps today. We're going to talk a little bit about Extrema, minimums and maximums. That's what Extrema really are when you talk about Extrema. I have a few examples about minimums. There are two types of minimums and two types of maximums. So I want to get us to look at that. I want to draw a picture right here. All right, like this. All right, and no numbers per se right now, but I do want to talk a little bit about what is a. Okay, let's draw this picture here. And I'm trying to draw it the way I drew it a while ago. Let's see here. Okay. Okay. This would be like a. Let's draw this. Let's keep this. Let's put an arrow on the end of this, meaning that this goes on forever. And we can do the same thing here. Okay. If we want, let's say, like a local minimum, this is, if you look at this side here, this is going down to negative infinity. This is going forever in this direction. So you can just keep on. This just keeps going. But you do have two local minimums here. Okay, one is here, and then one is here. And again, I don't have any numbers to show that, but that's okay. We just want to get the idea behind a local minimum here. So in this case, these two right here, all right, this one and, well, this one here, are local mins. All right, I'm just going to say mins for minimums. Okay. We can use the same picture to look at local maximums. Okay, so that's local minimums. I guess I could have just left that up there, couldn't I? And right here, these two right here are local, this one here, and then this point right here are local maximums. Okay, maxes. They're local because they're not what you call an absolute max. Okay, this is higher than this one, but this is not the absolute highest max. Just like these two, let's put down the word again, local mins. What is that really? These two are local mins. These are not absolutely the lowest points on the graph, because this side right here goes down to negative infinity forever, and of course this is much lower because, well, there's no end to it going this way. So these have to be what you call local mins, because they're not the lowest points on the graph. These points that go, there's points here that go forever this way. And so that would be the local. There's not what you call an absolute minimum, it's just a local minimum. And I'll talk a little bit about the difference between those two in just a moment. All right, local maximums, this going up this way is going up to positive infinity. So there's no way these can ever beat this. Okay. All right, so this right here, these two are local maximums. Okay, these are local minimums. Okay, all right, and that's kind of the idea behind this. Let's look a little bit now at what we call absolute absolute maximums and absolute minimums. And let's do this instead of putting this at positive infinity. Let's go ahead and erase this. Okay, and matter of fact, what let's do, let's just let's do this right here. I'm going to put a end point right here. Yes. Okay, and in this particular case, I guess I should go ahead and draw it on down and put an end point on the end of this. Okay. All right. Now, instead of that, that's not going to negative infinity. But now these are local minimums. This is absolute. These are called absolute max. This is an absolute maximum here. Okay. Absolute max. It is the highest point. Now, this endpoint, oh, I don't know, we could call this B, and then we could call this endpoint right here A. Alright, A is of course negative, but we don't care about that. It's from the interval, the closed interval, A to B. In this interval, we have four things here. Okay, this is an absolute, okay, absolute min. It is the lowest point. So absolute mins and maxes are the lowest and highest points on the graph. Okay, if we call this function f right here, f has all four. F has an absolute minimum and an absolute maximum. So this is the highest point on the graph. These are local maximums because they're not the highest points on the graph. This is the highest one here. And these are local mins because they're not the lowest points on the graph. This one almost catches up with that one. Matter of fact, just to kind of make it look a little bit better, let's just go a little further down, and we can make this one go a little further up just to kind of, okay, all right, there we go. And we'll just move our arrow right there. Okay, now we see that this is an absolute min, an absolute max, local maxes, local mins. Okay, I can do this right here, and if I make this hollow right here, I do not have an absolute max. Well, yes I do. Maybe this would be now the absolute. This is not a maximum at all now. Okay, this is not a max here. Okay, I could remove this right here and make this hollow right here, and the only minimum you got is right here. Well, you have this absolute min here, and you have a local min here, and right here you have, this would be your absolute max here. Okay, this is still a local right here, but this would be your absolute absolute max. Okay, all right, right there. Okay, now this is not even a max here. Okay, this is higher than this, but this is not an absolute max anymore now. Okay, and if I were to do this, if we were to just make this, wow, okay, let's do this right here. Make this hollow here. You don't have even a max. You don't have a local max. You don't have an absolute max at all, because these are hollow here. Okay, these y values are hollow. Okay, so there's no max at all. The only mins that you have an absolute min here, and you have a local min here. This one's not a min here at all now anymore. Okay, like this. Okay. Now, if we were to, okay, the only thing you've got now is just a local min. You don't even have an absolute min anymore. Okay, that's gone. That idea is gone. Now you do have a, but now here, if you do this, you don't have either. All right, in this case here, you have neither, neither. All right, we have neither a max nor a min. You don't have it. Because all of these are hollow now. Okay, you understand the difference now. Okay, I can give myself a max somewhere if I make this solid right here. Now I have a max, but I don't have a min. If I do this right here, well, right down here maybe, I have a min. Matter of fact, I have an absolute min, don't I? But I don't have, well, if I do this here, I don't have a max anywhere. I only have an absolute min. Okay, does that make sense, everybody? Okay, well, that's graphically what we're looking at, and that's what we need to get established from the start. I want to do the next segment of the lesson where we are looking for, well, we're looking for maximums and minimums and all that. And here's something that we need to pay attention to. All right. Okay. Let's look at what we call, first of all, let's just find local. Let's go with, let's see, I'm trying to see what I was looking for. Okay, let's just go with a local max, okay? And we're going to look at the closed interval from -7 to 7, okay? So what I want to do is I want to say f at x. And this is, now we're not looking at this, okay, graphically, although I could get a graphing calculator and graph this and show this. We're only interested on the interval from -7 to 7, okay? Anything there. Now, let me do something here before we get off into this. I want to share this with you. Let's say maybe we have something that looks something like this, okay? And maybe we have this, and maybe we have this right here, okay? All right, and maybe this is this is 0 here. Maybe this is well, let's say this is -1 here, and right here is 1, +1 right here, and then maybe let's scoot it over a little bit further over, and we'll say right here, okay, this is at 2, okay? Alright, and of course this is 0 here, okay? We're going to try to fix it up where it looks a little more, okay, I don't know, symmetrical. I don't know, that's still not exactly right, but you get the idea. Okay, well maybe the other did look better. Okay, it doesn't matter at this point. Alright, right here. Okay. This interval is from -1 to 2. Okay. When we're looking for a max or min, or an absolute max or an absolute min, here's our absolute max right here. actually this is at x equals 0, isn't it? Okay. So we have an absolute max at x equals 0. The endpoints, these are called endpoints right here, and here. Alright, endpoints. This is an endpoint, and this is an endpoint. Okay, bear with me just for a second. These numbers that are in between here are called a special name, critical number. This is a critical number. X equals 1 is a critical number. X equals 0 is a critical number. Okay, I'm just going to say CN. So when you are checking for absolute or local maxes, local mins, absolute max, absolute mins, you have to look at both endpoints. So we have to pay attention in this problem to -7 and 7. And we have to look at critical numbers. Okay? So this one right here, in this particular case, we have an absolute min at x equals -1. That's one of the endpoints. We have an absolute max at x equals 0. We have a local max at x equals 2, and we have a local min at x equals 1. So a lot of times students think that we have you have a max or min just only at the critical numbers, and a lot of times students will just look at the critical numbers. But when you're looking at Extrema on a closed interval, then you must look at the endpoints and the critical numbers. Okay? Okay, so we just have to remember to check, in this case, all four, and that's what we're going to probably have over here, because we're already looking at two numbers right here, -7 and 7. We have to look at that. Okay, so we're actually looking for a local max. Okay, and we're going to have to check all of them to see where the local max is. Now, let's take a look at this problem right here. Alright, so I'm going to erase all of this. And that's the idea behind Extrema. You have to check the endpoints and the critical numbers. Well, where did critical numbers come from? You remember all those derivatives we've been doing? We got it right here, okay? We're going to have to find the critical numbers, and it may be that we don't have. Maybe the derivative, well, I'll have to show you some other rules in just a little bit, but we're looking for the critical numbers. Critical numbers come from f prime, g prime. Okay, alright, well, we've got to take this derivative. First of all, let's rewrite this. F at x is equal to 1/3, that's a 1 in front of that, so 1/3 x cubed minus 9x. Everybody see where the 1/3 comes from? Alright, so now we're going to take this derivative. We're going to remember we put the 3 in front times 1/3. Now remember, we're reducing the exponent by 1. Keep that in mind. Remember, 9x is just 9. Okay? And look what's nice about this. This is 3 over 1. These divide out. Now you just have x squared minus 9. Remember, that is f prime at x. You want to set that derivative equal 0. Now what this represents, guys and girls and whoever else is looking at this, is the slope of the tangent line. Here is, okay, I'll draw this picture here. Here is, here's a critical number right here. Here's your endpoints right here, A and B. Oh, well, all right, that's your that's A here, and then B would be right here. All right, critical numbers would be somewhere like this would be maybe C right here, and this critical number is D. So in this case, you have your critical numbers between the endpoints A and B. C and D would be your critical numbers, but this is where the slope is equal to 0. That would be a horizontal tangent line right there. Okay, so that's basically what you're looking for right here, is to see where that crest comes up right here. Alright, so, and we could get into this idea that, well, what if this looks like this? Well, your derivative, it's still continuous, but the derivative here does not exist here at this number here, even though there's A and here's B right here. Alright, and you do have a max here, even though this derivative does not exist. That's called a cusp. Alright, and the derivative, sometimes even if the derivative does not exist, you still may have a max, or even if it's turned upside down, you still may have a min. So, alright, you have to kind of keep that in mind also. Okay. Alright, so now let's go with the problem here. We know that if we can do this by factoring, we can do it by the square root method, but I'm just going to go ahead and do it by the square root method. If we add 9 to both sides, here we go, we got x squared equals 0, and of course, guys and girls, if we get down to x squared equals 0, certainly we know that x has to be 0. Okay? If you take the square root of both sides, the square root of 0 is still 0. Alright, so we have, I'm sorry, this is not 0, it's 9. What am I thinking? X squared equals 9. X equals, now you got to remember, oh my goodness, what in the world was I thinking to say 0 plus 9 is 0? I don't have an answer for that. Oh my. But anyway, I find myself having to correct myself, and that's alright. At least I do correct myself. Alright, so if you take the square root of both sides, remember you introduce plus or minus. So look at this. We have two critical numbers. I'm just going to abbreviate. X equals -3, x equals 3, and we still got to try the endpoints. Now, what do we mean by trying all of this? Alright, this was the original problem. Okay, and here's what we got to do. My oh my. It's a good thing that I did all the work ahead of time. I am going to take this problem. Alright, so here we go. Let's say also critical number Cn, x equals -3, x equals 3. We also have the endpoints. Endpoints, I'm just going to do like this. Alright, x equals, we still got to try x equals -7, x equals 7, and we're only looking for a local max. Okay, that's what we're looking for. It is not going to be the highest number. but it's going to be a local max. Okay, so let's look at it. What you do with these numbers is you plug them in to the original problem. So here we go. We're going to try. I'm just going to go ahead and show you. F at -7 is -7 cubed over 3 minus 9 times -7. That endpoint, if I look at that answer, I will get, okay, I'm thinking that by doing the arithmetic, I will get a -154 over 3. And that is really equal to -51 and 1/3. 15 divided by 3 is 5. 1 is left over. No, nothing's left over. 4 divided by 3 is 1. And then you got 1/3 left over. Okay. So that's that. I'm going through this. And I'll just show you how I do one by hand. Okay, so this will be a -343. I'm not going to do any more. Over 3. This is already over 3. Plus a negative times a minus times a negative is positive 63. All right, now you want the same denominator. So since you have a 3 here, I'm going to introduce a 3 down here and multiply by 3 up here. Okay, like that. And when you do that, you get -343 over 3 plus 189 over 3, and that's where the -154 over 3 comes from. So -51 and 1/3. Alright, so I did that by hand. You can do it on your calculator if you want to. Okay, and you probably get 0.333333, which is the same thing as 1/3. Okay, let's do also, I'm going to do the other endpoint, and it doesn't matter what order you do these in. This is actually 7 cubed over 3 minus 9 times 7. Again, this is 51. Alright, so let me put this over here. This equals 51 and 1/3. So, right here. Alright. Let's look at F at 3, or -3. It doesn't matter which one we do. So, -3 cubed over 3. Did I do that? Yes, I did. Minus 9 times -3. Again, I think I've got that to be equal to 18. Alright, so let's box these in right here. Okay, there's that one, there's that one. Okay, and then finally F at 3 is equal to 3 cubed over 3 minus 27. Yep, minus 27, or 9 times 3 rather. Okay, 9 times 3, which is 27. And that is equal to -18. Okay. Now, we know, if we look at this very carefully, this would be an absolute min, wouldn't it? It is the largest negative of these two negatives here. So this would be the absolute min. That's in this interval here. This would be the absolute max, wouldn't it? Okay, in this interval here. This would be the local max, simply because even though it is a max, this max is higher up than this max, so this makes this a local max. This makes this a local min. And the deal is, we're looking for that value that gives us the local max. We're looking for a local max. It depends, students, on the question, doesn't it? If this said local min, you would be picking this one. X equals 3 is a local min. As a matter of fact, if you wanted to, this is actual, if you wanted to have the point now, if they're asked for the point, you would have -3, -18, and then this one right here would, +3, -18, this one would be -3, comma 18, this one would be 7, comma 51 and a third. Alright, and then this one would be -7 and -51 and 1/3.